All right, let's do some math. Barycentric coordinates. Yeah, what is this? Barycentric. Okay. Coordinates. Sounds complicated. I promise you, it's only moderately complicated. So if you have a triangle, you can describe any triangle using just two of the basis vectors of the triangle. Okay, and let's just put this guy at the origin just to make life simple, and then this one will be at, I don't know, let's say 5, 3, and then this guy will be at 2, 5 or something like that, and then you kind of implicitly have another line over here. Okay, and let's say that you have these 3 points, and you want to know what color this spot here should be. Okay, it's easy if it's a blue triangle like we have here, but what if, and just bear with me here, each of the vertices has a different color. So what if you have a red vertex, and you've got a green vertex, and you got a blue vertex over here? How on earth do you find out what color all these points should be? You remember this slightly? This is actually pretty cool. Good. All right. So you can tell that now if you just had a line, you would use a lerp, right? Because that's literally what lerping means, right? Like if you had a point here that's blue, and you had a point here that's green, you would want to lerp it, right? So at one end it's blue, at one end it's green, and then halfway in between. So the RGB value here would be 0 RGB, RGB. With a lerp, halfway in between would simply be 0, 0.5, 0.5, right? You just basically take half, you're halfway between the two, right? And you can do a color lerp, and this would be some sort of teal color or something like that. Or no, that's gray, actually. But it's going to blend from blue to green. How on earth do you do this with a triangle, right? Because you got 3 things. You have a 3-way lerp. And so it's not a lerp anymore. It's not a linear interpolation anymore. It's something harder. Okay? And so maybe you can see on the edge, it's still a lerp, right? Because here's blue, right? And here's green. And so like if we wanted to calculate the color here, halfway between it, do you guys see how that's kind of the same thing? Right? It's like, the color here would be 0.5, 0.5, right? Because it's halfway between the blue and the green. And here it'd be, blue's kind of hard to see. So if this guy's color is red, green, blue, this guy's color is red, green, blue, this guy's color is red, green, blue. This spot here is going to be 0.5, 0, 0.5. So on the edges, we can still use the lerp, and this spot here is going to be 0.5, 0.5, 0, right? But in the middle, how do we figure out the color here? How do we figure out the color here? That's a tricky question. This is something that bugged me for years until I figured this out. So how do we do this? I will tell you, because this is class and not a Socratic seminar. So let's say we want to figure out what color it should be here. First of all, what do you suspect the color is going to be close to? If you had to guess, is it going to be more blue? Is it going to be more red? Is it going to be more green? Like, if you just had to eyeball it, it's kind of close to the red-green edge. It's kind of far away from the blue. Least blue, semi-red, semi-green. Yeah. So it'd probably be, I don't know, little bit of blue. Yeah, there's a little bit of blue because we're like 80% of the way away from blue. So the blue might be like 0.2-ish. And then the red and the green might be, I don't know, 0.4-ish, something like that. If we had to guess, right? Do you guys see that? Because it's kind of like far from the blue, but kind of halfway between the red and the green. So here's how we actually calculate it for realsies. Watch this. I'm going to draw triangles inside of my triangle like this. That's a terrible straight line. Let me do that again. That. And let me get this X out of the way. We all know that's the point, right? This is the point we're talking about. How do we get the color here? And then I will draw a straight line from here. Actually came out straight. I'm impressed with myself. And let's get rid of these guys over here. Get rid of the distractions. Get rid of the distractions. This guy maybe will leave. I don't know. Okay. So this is going to form triangleception. So this is going to form 3 different triangles inside of the triangle. The amount of blue we get, here's the answer. The amount of blue that we're going to get here, the amount that's contributed by this guy down here, is equal to the area of the triangle opposite him. This area here. This area here is whatever ratio that is. Like if that's 10% of the overall triangle, then the amount of blue we're going to get is going to be 0, 0, 1 times 10%. In other words, we're going to have a 0.1 blue at the end of the day. Okay. So whatever fraction of area this triangle is how much blue we get, or whatever color we have down here. I'm just using red, green, and blue so you can see how they mix. In reality, they're probably not going to be primary colors. You just use algebra and mix them together. Okay. Just like you could lerp between things that aren't just pure blue and pure green, right? So how do we figure out the area of this? How do we figure out the area of the whole triangle? Okay. As it turns out, there's this thing called cross product. And these are words you're going to hear come up a lot in game dev. There is the dot product, and there is the cross product. And these things come up everywhere. Okay. So you can compute the area of something by using the cross product. The cross product actually gives you the area of a rectangle. So in order to get the area of a triangle, what do? Let me show you. So if you have a parallelogram that looks like this, okay, and you have vector A and you have vector B, if you take A cross B, this gives you the area of the parallelogram. Parallelogram. Okay. Yeah, don't call it CP, man. That's Child Protective Services. Means something completely different. Cross product and dot product are in calculus. They're in linear algebra. They come up everywhere. And they're actually really useful. Okay? So, and somebody's dumping gravel outside of my window. Okay. So how do we get the area of a triangle? Because the triangle we're forming is this. If we know the area of the parallelogram, let's say the area of the parallelogram is 8. What is the area? The whole thing is 8. What is the area of one of these triangles here within it? How do we go from an area of a parallelogram to an area of half the parallelogram? Yeah, divided by 2. Perfect. So if the area of the parallelogram is 8, the area of this is 4. And so the formula to get the area of a triangle is just A crossed with B divided by 2. And that'll give you 4 in this case. Okay? Cheese pizza. Cheese. All right. Yeah, that the whole pizza gate. Lord. Okay. So there's actually an optimization where you don't divide by 2, but we'll do the division by 2 for now. Because everything's a triangle, so everything gets divided by 2, and we're caring about ratios. We actually don't need to divide by 2, but we'll do it just to humor us. So what is the overall area of this triangle? Well, we have 5, 3, and we have 2, 5. So cross product, we're doing scalar cross product, right? The formula for this is x1, y2 minus x2, y1. And depending on which vector we pick first depends on whether we get a positive number or a negative number. So I'm just going to take the absolute value of this because we're doing area. So it doesn't matter which one we do first because a negative area doesn't make any sense, right? And so we got 2, 5 and 5, 3. So we have 2, 5 and 5, 3. So 2 times 5 minus 3 times 5 is 10 minus 15, which is absolute value of 5. So our triangle here has a area of 5. Okay. You guys understand? Oh, sorry. Divided by 2. So it's going to be an area, like I said, usually you just don't divide by 2 because when you do ratios, if everybody's divided by 2, it doesn't affect anything because it's a ratio, right? The ratio of 10 to 20 is the same as the ratio of 5 to 10. You know, it doesn't matter if you divide by 2. It just slows things down. Okay. So, do you guys want me to divide by 2 or not? Actually, I already have 5 written down here. Divide by 2 can also have issues with rounding. No, you don't want me to do it. Okay, I'll just leave it as the rectangular area. So it'll make the numbers easier too. Okay, so what is the area of this little blue triangle here, right? We've got 2 basis vectors here. We got 1 here. We got 1 here. So this point P, I'm going to have to come up with a coordinate for it. Let's see. 1, 2, 3, 4, 5. So this guy's like about 2 across. Maybe, yeah, 2 across and 2 up, maybe. I don't know if this is to scale, but we'll say 2, 2. So how do I get this vector and how do I get this vector? How do you get a vector? How do you get a displacement vector between 2 points? A displacement vector means starting here, how far in what direction do I have to walk to get here? So we'll call this point A, we'll call this point B, we'll call this point C. How do I get the displacement vector from B to P? How do I get that vector? Destination minus start is correct. So this is going to be P minus, I don't know if you can read that. That's a B there. Yeah, there. Okay, so P minus B. And so P is 2, 2. So it's going to be 2, 2 minus 2, 5. That doesn't sound right. Now this guy's going to be bigger than 2. Let's make him 3 then. Okay, so it'll be 3, 2 minus 2, 5. And that gives us an answer of we're going to go 1 to the right and 3 down. So you see that? This is 1 unit right, 3 units down. Again, it's not really to scale very well, but whatever. We're just pretending. So we have a vector pointed 1 right, 3 down. That's this. Oh, let's not erase it. That is this displacement vector right there. Okay. And then we've got a vector. You know what? I am going to delete this guy in the middle here. It's just creating a little bit too much mess. And I don't need these colors anymore because we know what the colors are. Let's erase these colors, clean it up a little bit. Okay, and then we want C minus B as the other one. So C minus B is the other basis vector. So that is going to be 5, 3 minus 2, 5, which means we travel 3 units right. As you can see here, this is 3 to the right, and it is 2 down. So just 3 right and 2 down. Okay, so if we take the cross product of 1, negative 3 and 3, negative 2, so it is 1 times negative 2 minus 3 times negative 3. And so that is negative 2 minus 9, which is plus 9. Which is, that doesn't sound right to me. No, it's 3, negative 2, 1, 2, 3. Negative 2 is negative 2, negative 2 minus 9. I might have bad coordinates here. Let me see. Is this wrong? 3 to the right. 3 to the right, 1 to the right, 2 down, and 3 down. I might need to make the y coordinate of P3. Yeah. Yeah, I think we might have something actually outside the triangle. Yeah. Okay, let's do that. There. And so that'll make it down 2 instead of down 3. So negative 2 times 3, negative 6, and that'll be a value of 4. Okay. So this guy is going to have an area of 4 here. And then we can do, I probably should have gotten graph paper out and done this, but, and then we can compute the area of the other things if we want. But where the numbers aren't good. It's 1 to the right. It's really more. Whatever. Okay. It's not to scale. Okay. So this guy is 80% of the size of the whole area, apparently. Did I do this right? I don't think I did this right. 2, 5, and 5, 3. 2, 5, 5. Oh. Oh, 2 and 5. 2. Yeah, I had these. Okay. Yeah. 2, and then 5, and then 5, and then 3. That's why. Okay. That's why I wrote the x and the y backwards. Okay. 25 minus 6 is 19 is the actual area of the rectangle. Okay. That makes a little more sense. Because I was getting a really small number. Always double check. I have 19. Okay, so this is 4/19 of the total triangle here. And so the amount of blue we get is 4/19 times red, green, blue. That's the blue component of that point. You do the same for the red, you do the same for the green, and you will get an RGB value for that point on the triangle. You do that for every point on the triangle, and you can color in a triangle smoothly interpolating between all 3 vertices. Okay? So if you want to figure out the red component, you guys want to see that? Yeah? Do you guys want to see how to compute the red component? This is the blue component, right? The amount of color we get from vertex A is this. You guys want to see how to compute this one too? Same process. So the area of this zone here, whatever proportion this red zone is here, is the fraction that the color of this vertex contributes, which is in this case is just red, which makes it easy. So the basis vectors would be 3, 3, and 5, 3. And so x1, y2 minus x2, y1. This is x1, this is y1, this is x2, this is y2. So it is writing them down this time. 3 times 3 minus 5 times 3. It's 2, y1. So it's 15 minus 9 equals 6. So the amount of red we have is equal to 6/19 times RGB. So we're going to have 6/19 red, 4/19 blue, and then the remaining fraction will probably be 9/19 green. But let's just do the math and make sure it works out. Or I could have made a calculation error again. Who knows? Anything's possible. And so to calculate the fraction of green, what we want to do is figure out what relative fraction this subtriangle has. And whatever proportion this subtriangle has is the proportion that it'll be green, or whatever color we have on this point here. Just green in this instance. Okay. So the basis vectors are this one, this line here, and this line here. And so we have a 2, 5, cross-producted with a 3, 3, x1, y1, x2, y2. Again, I'm just writing everything down so I don't screw up again. x2, y1. x1 is 2, y2 is 3, minus x2 is 3, y1 is 5. 15 minus 6 is 9 again. So 9, yeah, perfect. Okay. So the amount of green we have is 9/19 times the color of green, RGB. Okay, so you see 4, 6, and 9 add up to 19. So the blue triangle here is 4/19. The red part here is 6/19. Let's see if I can get a better color there. and the green fraction is 9/19. So these are the relative fractions of these three subtriangles. The amount of color that the points contribute is equal to the size of the color opposite them. Because the nearer the point is to you, the bigger the triangle is on the other side, right? Like if we had a triangle like this and a point here, this point here is going to contribute the most to the color because see how big that, see how big this triangle is here, right? So it relatively speaking has the greatest fraction of the area of the subtriangles, and so this guy's color is going to dominate over the other ones. The other ones are going to contribute a little bit, equal to whatever fraction this is for this guy, and whatever fraction this guy is for this guy. And that is barycentric coordinates. And you can use these for everything, like texture mapping. If you have a picture and you want to put a picture on a triangle, you want to know how close you are to each one of the points. You know, anytime you want to know where you are on a triangle, this is called a barycentric coordinate system. It's kind of like a 3-axis coordinate system. Like I'm close to red, I'm close to green, I'm close to blue. It's not like a X and a Y exactly. It's kind of like where you are on the triangle itself. And it's kind of fun. So if you want to look at the barycentric coordinates, I think Megan's already done this already because she's just really on top of the ball. I don't remember where I put my my demo code for it. 3D animation. There we go. All right. So you can see there, it's clearing the screen and drawing. It's moving the pixels around. And here, let me get my face out of the way. So you can see it's moving the pixels around, and it's smoothly interpolating the colors as the pixels kind of animate around the screen. Now you can see I've got one that's kind of like a variety of red and brown colors. I've got one that's just the pure red, the pure blue, the pure green, and you can see kind of how the colors interpolate across them. As the triangles overlap each other, you can see it's sometimes drawing one of the triangles in the front and sometimes drawing one of the other triangles in the front. And the reason for that is because I've already added depth to this. So that's actually the one assignment after barycentric. Barycentric is just doing that color interpolation between A, B, and C. For this animation assignment, you actually have a depth to everything. And so if the triangles penetrate each other, you will sometimes see one of the triangles on top and the other on top, depending on which one's closer to the camera, right? If this one's closer than this one, you're going to see this one. And so that's what you're seeing there. But you can see it's doing barycentric coordinates to interpolate the colors. More time. And you can see this is pure green. This is pure red. Pure blue is off the top of the screen here. And you can see on the edges, it smoothly transitions from green to red. On the right edge, it transitions from green to blue. And then in the middle, it's like a mixture of all of them. And so that is a barycentric interpolation of colors. Yeah, that's exactly right. So yeah, that's why I didn't send out the source code, because you guys get to do this. So that's your learning for today. But you don't have to code anything along these lines for a little while yet. Okay. So I'm not evil. Just it's a good programming exercise. Yep. It's a good programming exercise to do this. So there's a little bit of vector math, a little bit of cross products going on. A lot of cross products actually. You're going to do cross products constantly, and add them together and take ratios and multiply and interpolate and things like that. But it's not too bad. Every villain is lemons. Okay, so that's it for today, guys. Thank you for coming out. Have a good time at work, Megan. I know you got a jet. Voss, make sure that you do your homework. All right, see you guys on Tuesday. Peace.